All right, happy Thursday. We're in week 3, right? So next week, at the end of next week, will be the halfway point. Summer term moves so fast. So I didn't look who finished the test, but I want to remind everybody it's due by midnight tonight, actually 11:59. Please don't start it at 10:30 because sometimes there are issues with software, computers, internet, things like that. And um, I don't check my internet late at night because I'm an old lady and I go to sleep. So make sure you are getting that done. And the Respondus people have decent support, but you have to email them and then have to wait for them to email back. So try not to wait till the last minute. Today we're going to look at chapter 5. Chapter 5 is going to feel completely disconnected from everything we've done so far. I don't think I will a single time mention the words mean, median, um, interquartile range, standard deviation, or any of that. So it is going to feel completely separate. You'll see next week where I'll be making some connections with section or chapter 5 and then the future ones. Because pretty much what happens is the first 4 chapters are the statistics part. Today we're going to start on the probability part and we will be combining them, but we're going to start on the probability. So we need the basic terminology and all of that for probability. So that's what we're going to do today, is we're going to learn about probability. We're going to learn about the basic rules and the vocabulary. Start with chapter 5.1. We're basically with 5.1, we're going to be talking about the empirical method versus the classical method. And I've always had different words for them because I learned in California public schools many, many, many years ago. And those are the words that stick in my brain still from when I learned it when I was a kid, but I'll probably still give you those. And chapter 5.2, be talking about something I call OR probabilities. We'll be talking about the addition rule. We'll talk about what we do, the complement rule. We'll talk about when things are disjoint, when they're independent, and then what independent, not yet. We'll talk about when they are not disjoint. And then 5.3, we're going to be working at what I call and probabilities. We're going to determine if 2 events are independent, talk about what makes them independent. And then we will learn about the multiplication rule and at least probabilities. The words at least become very important. There is no lab. There is no lab at all this week. So little break on the labs and the Excel. I'm hoping you all are happy about that. Even though I love the labs, I love looking at the different types of data that you come up with. Some of it's really interesting, and especially the correlation. There's things that I think are correlated, and then I see somebody do their lab on them. I'm like, wow, I expected something very different there. So I'm very entertained by them. So there's that. Oh yeah, and also since the test closes tonight, I will start grading them tomorrow, but I usually don't get them done until about Sunday morning. Once I get all of the tests graded, once everything is graded, I will open them up for you to look at feedback. So you won't be able to see any feedback. You'll only see your grade until probably Sunday or Monday. So don't freak out if you can't click on it and go in there and look at feedback. So Sunday or Monday is when you should be able to access that. So, okay, that's it. Let's get going. Okay. So we've used the word probability all our lives. You probably said something today like, hey, the probability of that happening is pretty high or something like that. Or maybe even the chances of something happening. You might have used that instead, or the odds. All of that is about probability. Odds is slightly different, but we're not going to get into that. So outcomes of probability. I am never going to have you list all of the outcomes because as you can see here, it's tedious. It's a lot of work. So like, for example, the outcomes of rolling the dice. So outcome 1, we have lowercase e and then a subscript of 1. So our first outcome is rolling a 1. Second outcome, rolling a 2, and on and on and on. Listing them out like this. So think about if you had to list all of the outcomes of pulling cards out of a deck of cards. That would be 52 different outcomes that you could have. That would take you a very long time. Flipping a coin, no big deal. E1 would be flipping heads and E2 would be flipping tails, and then you're good. But letter B, the sample space, is all of the possible outcomes, and you will have to do this. I can tell you on your next test, which since it's summer, it's going to come up quicker than it's going to be week after next. Unfortunately, because it's summer, we have 2 tests left, and we only have 5 weeks left. They're going to come quick. So week after next, week 5 will be your next test. It will be on chapters 5 through, I believe 5 through 8. Okay. Anyway, might be 5 through 7. I don't know. We'll wait on that. Anyway, so all possible outcomes is every way it possibly could land. So if I was rolling 2 dice, it would be 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. So there'd be 36 different things that I would have listed here. But this is 1 dice, so there's just 6 outcomes. So we just list them, put them in brackets. It's a capital S. I know that it looks just like sample standard deviation, but this is a capital S, trust me. Just love when we use letters that it's hard to tell if they're capital or lowercase, but I didn't come up with them. They just are. So you do S equals and then do your brackets and list all of the possible outcomes. That is a sample space. On C, we define our event. So defining an event is whatever you want to happen. That's your event, whatever a success would be. So if my event is, I want to know the probability of rolling an even number, all of the things that would be a success would be 2, 4, and 6. So the event I'm looking to happen would be rolling a 2, 4, or 6. There's a capital E for event. So whatever the success is in your trial, that would be your event. So here, event is rolling an even number. So 2, 4, and 6. If my event was I want to flip a heads and count how many times the coin lands on heads, then H would be my event, or flipping a heads. All right. Before I go to the next screen, I want to talk about the sample space of if I do 2 things at one time. So let's say that my sample space, I want to know all the possible outcomes if I roll a dice and flip a coin. So all the possible outcomes if I roll a dice and flip a coin. So this sample space, so I'm going to put roll dice and flip coin. So this is just an example. So I would have S equals curly brackets. My curly brackets are really ugly. So I would have 1H, 2H, 3H, 4H, 5H, ran out of room, 6H, and then I'm going to have 1 tails, 2 tails, 3 tails, 4 tails, 5 tails, and 6 tails. That's a really ugly curly bracket, but that's what that's supposed to be. Let's try this again. This is a T, and that's my curly bracket. All right. So notice how now I have 12 things. And each thing, so I roll a dice and flip a coin 1 time, I can get any of these outcomes. So I could have a 1 paired with an H, and I can also have a 1 paired with the tails. I mean, it's okay if you flip them and say H1, H2, H3, and it doesn't matter what order you put them in necessarily, but these are all of the possible outcomes. So you have to account for every single outcome. I can't just put 1 through 6 and then H and then T. I have to put all of the different possibilities that I can get. Any questions on sample space?
So for the dice, you're saying that there's 6 sample spaces because of the dice. On each side, there's either a 1, a 3, a 4, a 5, or a 6.
Right. So there's
Okay.
six different ways the dice can land.
Okay.
Yeah. Right. Any other questions? Right. Let's move on. So the empirical approach, which is also, I've always called it experimental probability. So it's empirical or experimental. So this actually requires you to perform the experiment. Experimental probability is the way I learned it. And so I might jump back into that language. I just want you to know experimental and empirical, they're exactly the same thing. So this is one where you actually do the trials. You actually roll the dice 50 times. You actually flip the coin 100 times or whatever. Every time I flip the coin or roll the dice is one trial. So every time I perform that experiment, it is one trial. So in order to calculate this probability, it's based on your observations, based on your experiment. So the denominator is how many trials, how many times did you flip the coin, or how many times did you roll the dice? So that would be your denominator. Your numerator is how many successes you have. So for example, let's say that I'm looking for the number of times I roll a 4 on the dice. And I roll my dice 100 times. That is not a pen. I roll the dice 100 times and I get a 4 16 times. When I rolled the dice 100 times, I got a 4 16 times. Then that would be 0.16 or 16% of the time I rolled a 4. That would be my experimental probability. So the number of trials, the number of times you roll that dice or flip the coin or perform whatever experiment is, the number of trials is your denominator and the number of successes is your numerator. So that's the empirical approach. You actually have to do the trials. Or I know I said I wasn't going to do fancy schmancy calculator, but I'm going to show you. I didn't, you don't have to do this, but I'm going to show you. This is something that I learned on my calculator. Like during this past year, one of my high school students found it and showed me, and I was like, whoa, I never even clicked there. Okay, maybe I'll do it. So I don't click a lot of the buttons on my calculator because they're not what I'm looking for. So if it's not what I'm looking for, I kind of ignore it. But if you click on apps right here, there's a whole bunch of really cool stuff in here. So if I go down to probability, ProbSim, it's not going. Okay, you go down to ProbSim. I don't know why it's going so slow. You can simulate tossing coins, rolling dice, picking marbles, spinning spinners, drawing cards, random numbers, all sorts of things. I don't know if the TI-83 has this. My TI-83's batteries died and I haven't put new ones in it yet, so I haven't been able to look at it. But I know that I believe all the TI-84s have these, and it is just really cool. And also you can seed. Remember I told you that, remember we all got the same random numbers? You can actually, these buttons right here, these buttons on the top are the things you use to choose the things. So I can seed it. I can just put a random number in there. To seed it, you just put a random number in there, and then it's going to start you at that point in the algorithm. That way everybody doesn't get the same random numbers. And then I'm going to click this button, this F5 button right here, and it'll get me back to my random numbers. So I just seeded my calculator. Yeah, my calculator's not working great. It's a good thing. We don't really need this calculator today. Okay. So I want to get out of here, but I'm just going to close the window because it's not being nice to me. All right, let's go back. All right. So as this says, this relies on empirical evidence and it's based on outcomes. So we're going to do some examples. I don't know if anybody's ever played Pass the Pig. So after teaching this class, I had to go buy the game Pass the Pig. And in my high school probability or stats class, we actually played Pass the Pigs. I made them do it because it was fun. So the probabilities of getting different outcomes when you roll some pigs and they land different ways, you're trying to get them to land certain ways. And so 52 students rolled the pigs 3,939 times. And so here's the different outcomes. So this is not necessarily raw data, but it's pretty raw. So I just put it in a table, a frequency table, but we're going to actually calculate relative frequency and probability are actually the same thing. We're just changing the name. Just changing the name, changing it from relative frequency to probability. So all you do is you just take the number of times it landed that way. So 1344, I need a pen. 1344 divided by the total number of times we rolled the pigs. And then you just get what that decimal is. So this is 0.34 approximately, or about 34%. Personally, I don't care if you answer it as 0.34 or 34%. My open math will tell you how it wants you to put it in there. So if it has a percent in its answer it as a percent. If it doesn't have the percent, then you probably put it in as a decimal. Sometimes it'll say put it in a simplified fraction. So I can show you how to do that with your calculator as well if my calculator is nice to me, but I'm not going to do that right this moment. Okay, so each of these, I'm just going to calculate that probability. So I have 1294 divided by 3939. 0.33 approximately, 767. Can you just round to the nearest? I just am rounding to the hundredths place. There's not some rule about where to round, but that's just where I'm rounding. I think usually we'd round to 4 decimals, but I really am just kind of showing you at this point what we're doing. And apparently I can't use my calculator correctly. I put something really weird in there. Mm-mm. 0.03. And finally, 0.008. I had to go 3 decimal places on this one. All right. So by looking at this, we can see that to roll a trotter, there's about a 9% chance of rolling a trotter based on our data. So generally, if we're going to try to apply it to the population, to we would want to use a large number of trials. 3939 is a pretty large number of trials. So I could say with some certainty that we're probably about a 9% chance of rolling a trotter, about a 3% chance of rolling a snouter. Now, if I only rolled the pigs one time for each student, 52 times, I probably wouldn't be so certain. But as you repeat something over and over and over again, you are going to expect that you're going to get close to like what the real probability is. For example, if I rolled a dice thousands of times, I would expect to see that the number of times I rolled each number would be about the same. All right, let's move on. Let's do some actual things with these numbers. I've still got the numbers in here. I typed them in. Your notes that you have probably don't have them typed in, considering I just typed it in this morning. So we're going to use we built a probability model. So what a probability model has is exactly like a, what did we call it before? Did I call it a probability distribution model? I don't remember what I called a relative frequency table. Anyway, all of the probabilities have to add up to 1. So all together, I have a 100% chance of rolling one of those things. Just like if I flip a coin, there's a 100% chance. Okay, probably not 100, because I mean, I guess that there's probably a really small chance of it landing on its edge. But let's say 100% chance of getting a heads or a tails. There's a 100% chance if I roll a dice, I'm going to get a number 1 through 6. A fair 6-sided dice, there's a 100% chance that I'm going to roll that 1 through 6. So these have to add up to 100. And all of these are going to be between 0 and 1, because 0% probability would mean something can't happen, but 1% probability means it has a 100% chance of happening. There's really no such thing as 105% probability. There's no such thing. It's not real. Okay. So letter B, we're going to estimate the probability that a thrown pig lands on the side with a dot. So that puts us right here. So the probability it lands on a side with a dot is 0.3285, or you could say about 32.85%. So that's really, we already calculated it. That's what it is. So you just turn it into a decimal or into a percent, because most of the time we say there's a 32.85% chance. You'd say about a 33% chance. You don't usually say 0.3285, but you can say it here. This is a safe space. You can say it here. All right, finally, this is probably the somewhat new information. Would it be unusual to throw a leaning jowler? Leaning jowler, I get another color because I want to, is right down here. So for just a moment, take out the information at the file cabinet in your brain, take out the information about the empirical rule. You probably recall, according to the empirical rule, 95% of our data lies within 2 standard deviations of the mean. So that means 5% of our data is outside of 2 standard deviations of the mean, right? Does that make sense? And anything that's outside of 2 standard deviations of the mean is considered an outlier. An outlier means it's unusual. Therefore, if we have a probability less than 5%, it is considered unusual. So here, I have that 0.0081. It is less than 0.05. Therefore, throwing a leaning jowler would be unusual. Because it occurs less than 5% of the time, it's considered unusual. Let me tell you, I've never thrown a leaning jowler. A couple of my students did. I've never thrown one. I tried. I tried for quite a long time. I've never thrown one. But I mean, we literally have less than 1% chance of throwing a leaning jowler. So there you go. Questions before I move on? Right. Flip to the next screen. All right. So 200 people, 200 people were asked their means of travel to work. I would like you to build a probability model. So out of 200, each of these is out of 200 people. So I would like you to build this probability model. I am going to work quietly behind you, but I would like you to do this. So calculate all of those probabilities like what I did on the last, in the last set. And I'm going to work quietly behind you with my own little calculator. And if you get stuck, you can look up. All right, hopefully you got all these done. I only got it done so quick because it was 200, so I was able to just divide them all in half and move the decimal place 2 over. But this is something that after you've done it a while, you just kind of just do it. So if it took you a little bit longer and you had to put all of them in your calculator, no worries. I've been teaching math for a while. It's kind of just in my blood now. So now we need to talk about what the probability is that a randomly selected individual carpools to work. So figure that one out. This would be this one right here. So you could either say 0.11. How do I not even have the chat up? What the heck is wrong with me? Pull that up. There we go. 0.11, or you could say 11%. I'll take either one. Okay. Now it says, would it be unusual to randomly select an individual who walks to work? So the walking to work person is right here. Uh-oh, that was weird. We'll just leave it. So the walking to work is right here. Would that be unusual to randomly select a person? Yes, it is less than 5%. Therefore, it's considered unusual. See if I can get my calculator working again. I'm going to show you something magic for simplifying fractions. Let's see if my internet's been weird all day on my computer, and I probably should have restarted before class, but you know, sometimes I'm lazy. Okay, let's quit. Yes, I want to quit. All right. So let's say that you have a fraction you want to simplify. I'm going to say I want to simplify 248 divided by 1600. So I love simplifying fractions, and I could do this pretty quickly, but sometimes my brain isn't working correctly, or sometimes we just want to work smarter, not harder. So if you put a fraction, you put this fraction into your calculator, you want to simplify it, you hit this button right here, this math button, and just choose the first option that shows arrow frac, then hit enter, and then hit enter again. It will simplify your fraction for you. Is 31 over 200. So like 528 divided by 1286. And I want to simplify that fraction, hit math, enter, enter, and it simplifies your fraction. And that also works like if I had a decimal, so if I had 0 point, I know what this one is. Obviously, I have, whoops, that's not what I wanted. I want that 0.125. I mean, I know that's 1/8, but I want to turn this into a fraction. Hit math, enter, enter, and it'll turn it into a fraction for you. So your calculator can do fantastic, amazing things. There you go. That's not where I want to be. All right. So the classical method requires equally likely outcomes. So the classical method is also called theoretical probability. So we can't use the classical method for the pigs because the pigs don't have equally likely outcomes. However, rolling a dice or flipping a coin, those have equally likely outcomes. So then we can just use math. We can just use theory rather than performing the trials. You're doing something that every outcome has an equally likely outcome. Every outcome is equally likely is what I meant to say. Then you can just use math and say, this is the probability of it happening. So that's the theoretical probability because you don't actually have to perform the experiment. So dice, cards, coins, things like that, the things that are equally likely to happen. So that's theoretical or the classical method. I don't think that my open math is going to is going to use any of this vocabulary. It's just things I use, things I say. I generally don't say classical method. Theoretical probability makes more sense to me because it's theoretical. So the way that we compute using this method is the denominator is how many possible outcomes. So if you're rolling a dice, there's 6 possible outcomes. And how many ways can our event occur? So remember, the event is whatever our success is. So when we were looking back at that other screen, it was rolling an even number. So rolling a dice has 6 possible outcomes. There's 6 different ways your dice can land. If I want the event rolling an even number, 3 of those numbers is even. Obviously, I'm going to simplify my fraction because I can't handle just looking at it saying 3/6. So it's just because every outcome is equally likely, I can just math it. We just call it good. So this is the theoretical or the classical method. You just math it out. So you don't have to be throwing dice or throwing pigs or any of that stuff. No, throwing pigs is fun. It would actually, the nice thing about the pigs game, I should have brought it home over summer. It doesn't require anyone to do any, well, it requires one person to do reading, but it's a great one to play with small kids past the pigs because they just have to roll them and look at how they landed. And it's all pictures. Okay. I have a fun-sized bag of M&Ms. The M&Ms, the bag of M&Ms contains 9 brown candies, 6 yellow candies, 7 red candies, 4 orange, 2 blue, and 2 green. So every M&M in the bag, every individual M&M has an equal probability of being chosen if I'm randomly choosing an M&M out of the bag. Yes, there are more brown than there are green, but still every single M&M in the bag has an equally likely chance of being chosen. So let me see how many's there. There's 15, 22, 26, 28, 29. So there's 29 M&Ms in the bag. We want to know the probability of choosing a yellow. Is it 29 or did I mess up? 22, 26. No, it's 29. Okay. So choosing a yellow, there are 6 ways that I can get yellow. So it would be 9 out of 29. 29 is prime, so there's no simplifying that fraction. But this is approximately 0.31, so about a 31% chance of drawing a yellow one out of that bag.
Where did the 9 come from?
9 brown. Okay.
Oh, I thought it was
Oh,
yellow. So when you say,
yeah, okay.
okay.
Sorry, is there 30? Did I calculate that wrong? So with yellow 7. Did I do that? I'll have to I'll count them again. We'll count them again. It's possible there's 30 and I just can't count. Which I always say that I can't count. Let me see. 9 plus 6 is 15. 15 plus 7 is 22. 22 plus 4 is 26. Plus 2 is 28. 30. Why the heck can't I count? Thank you so much. Yeah, I can't count. That is the thing I should be able to do, but you'd think as a math teacher, we lose some of our basic math skills when you learn the more complicated stuff. I've learned some really complicated stuff. So some of my basic math skills are gone. All right. Thank you. Okay. So now we want to know the probability that it's blue. Now we determined that I can't count. So the probability it's blue. So I have 2 blue candies. I have 2 blue candies out of 30. So that's approximately 0.07. So about a 7% probability of pulling a blue out. Is there 2 blues? Yes. I just wanted to make sure that I looked at everything correct. And there's 7. See, somebody didn't tell me that it's 6. Man,
Oh,
I
yeah.
I think that I just need to go back to bed and try again. My goodness. I really can math better than this. I swear I can math better than this. Okay, regardless. So there's all the letter C, all we're saying is you're 3 times more likely to pull a yellow out of the bag than you are a blue. If you did your math right, I apparently can't read or do math or anything, so I should just call it a day. But I won't. We'll continue. It'll get better from here. I hope I didn't confuse anyone with me doing the math wrong. Okay, let's move on. All right, let's look at dice. So we're going to look at the probability of rolling a 7. One thing I love, love, love about the diagram here is that things are on diagonals. So my 7s, and that's not a really good one. So my 7s are all on this diagonal right here. They're hard to see. I need to just circle it. So all of these are 7s, and there's 36 different ways that rolling 2 dice can land. But that all the 7s are on that diagonal. So out of 36, I have 1, 2, 3, 4, 5, 6. There's 6 different ways that I can roll a 7 out of the 36 ways. So we would just do 6 divided by 36. So we have about a 17% probability of rolling a 7 if I roll 2 dice. So I've had several people, I think that the older and older I get, the fewer people know what snake eyes is, because I think a lot of people don't say it anymore. But snake eyes is just double ones. I've had a few classes in the recent past where people didn't know what it was, so I need to point that out. Snake eyes is double ones. There's only one way. So it's just 1 out of 36. There's only one way to roll snake eyes. So about a 3% chance of rolling snake eyes. So I wouldn't count on it. If you're trying to win a whole bunch of money rolling snake eyes, I wouldn't count on it. And all the letter C means is you just look at the fact that you're 6 times more likely to roll a 7 than you are to roll snake eyes. So any questions on the classical method or theoretical probability? All right, I can move on. We are now in section 5.2. 5.1 went really quickly. So let's talk about disjoint events. So two things are disjoint if they don't have any outcomes in common. We can call them mutually exclusive. So if I'm rolling a dice one time, I can't have both, the answer can't be both a 3 and an even number. These things cannot occur at the same time. They're mutually exclusive or disjoint. So the beginning of this, we're going to talk about disjoint events, and then we'll go into what if they aren't disjoint, what if they aren't mutually exclusive. So we're going to first start talking about if they are. So I call this the OR rule for probabilities. So you're looking for the probability that one thing happens or another thing happens. So this or that. So the probability of rolling a 3 or an even number. So there's 4 different outcomes for that. And you would just add them together. So I would take the probability of rolling a 3, which would be 1, or would be 1/6. Woo! So probability of rolling a 3 would be, I don't have a pen again, 1/6 plus the probability of rolling an even number, which would be 3/6. So my probability of rolling a 3 or an even number would be 4/6 or 2/3. So the or probabilities, if they are disjoint, if they are mutually exclusive, you just add them together. You just add the two probabilities together. So let's do an example on that. Does anyone need me to stay here for a minute longer? Okay. So if I had a ton of different things, if I was pulling things out of a deck of cards and I said, what is the probability of pulling out a 2 or an 8 or a 9? There's 3 things. I would add all 3 of those probabilities together. So if I had a 20-sided dice, what's the probability of rolling a 5 or an 8 or a 16 or an 18? So no matter how many you're doing, you just keep adding them all together. As long as they are all disjoint, it's called pairwise disjoint. If none of the things can happen at the same time, then you can just add them all together. Okay. So this is another probability model. So this one shows that the number of rooms in a housing units in the US. So you're not going to have a 3-bedroom house that is also a 1-bedroom house. It just doesn't make sense. So these are all mutually exclusive. The way that we can tell that it is a probability model is that if I add them all together, I get 1, which I'm showing you right here. I added them all together, I got 1. And then all of the values are between 0 and 1. I can't have a negative probability. I can't have a probability higher than 1. Therefore, this is a probability model. Okay. So let's look at the probability of selecting a housing unit randomly, and it either has 2 or 3 bedrooms. So I'm going to look for the probability of getting a 2-bedroom plus the probability of a 3-bedroom. So the probability of getting a 2-bedroom is 0.032. The probability of getting a 3-bedroom, 0.093. They are mutually exclusive, so I can just add them together. So that the probability of 2 or 3, 0.125, 1/8, or 12.5%. So it's that simple. If they are mutually exclusive, you just add them together. Questions? Right. Move on. Make sure you holler at me if I move too fast. I don't know why. So I have some weird highlighter on here. Sorry about that. I'm going to ignore it and pretend I don't. We're just going to use a pen. We're going to look at the probability of drawing a king. So the probability of drawing a king. So here's a king right here. I don't know why they're weird colors also, because before I printed them to PDF, they were red. The red cards were red before I printed it to a PDF. Then I printed it to a PDF and they all turned blue. I don't know how. My computer just did something weird. Okay, so there are 52 cards in the deck. 4 of them are kings. So my probability of drawing a king is 4 out of 52, which is 1/13. That should be a 13. That's approximately 0.077%. Okay, so now I want to know the probability of a king, a queen, or a jack. So there's the queen, the king. Here's the king or the queen. My words don't work. There's the jack. They all have the same probability. So I could do 452 plus 452 plus 452. They are mutually exclusive because I'm not going to draw a king that is also a queen. So this is 12 out of 52, which equals 4/13, which is approximately 0.31 about. So we have about a 31% chance of drawing a face card if I drew a random card out of a deck of cards. Questions on disjoint or mutually exclusive events? Okay, we're going to tackle, not disjoint. We're going to tackle when they have things in common. Here is our new rule. If 2 events are not disjoint, then you add the 2 things together, then you're going to subtract where they overlap. You're going to subtract where they both have something in common. Subtract, I'm going to show you, don't worry, I'm going to show you visuals of it. You subtract the overlap. So you take the probability of E happening, the probability of F happening, and then you subtract where they overlap. I'm going to do it with cards and dice in a minute, and hopefully that will help. I'll give you a second to write down the formula, and then we will do an example. Okay. Here's my weird blue deck of cards. But diamond's still diamonds, so we're good. Okay. So we want to know the probability of drawing a king or drawing a diamond. So once again, here are the kings. These are the kings. I'm going to use a different color because blue is going to show up well. Here are the diamonds. Right there. Notice this one right here is circled 2 times. So if I do 4 out of 52, which is the king, plus 13 out of 52, which is the diamonds, I am counting this one right here 2 times. Woo! I'm counting this one twice, right? It is in both those spots because I counted it in the 13 and I counted it in the 4. Therefore, I have to subtract off the extra time I counted it. Because I counted it twice, I have to subtract off where it was counted the second time. Therefore, because I was at 17, so I'm at 16 out of 52. Because 4 plus 13 is 17, minus 1 is 16. And that does not look like a 2 at all. So this is approximately 0.31. So once again, there's about a 31% chance of getting a king or a diamond, because either one of those things is a success. If I draw either one of those things, it's a success. I could draw a 4 of diamonds and we're good. I could draw the king of spades and we're good. Questions on non-disjoint before I have you do an example? So you subtract the overlap. I'm going to write the word overlap on here. This is overlap. This is where they overlap right there. We're going to do dice. Okay. Mine looks a little different than yours. I changed it and I apologize, but sometimes I change things up a little bit. So we want to compute the probability of rolling a multiple of 6 or rolling doubles. So let's start with where the doubles are. There's the doubles. The multiples of 6. Multiples of 6 would be 6 and 12. So my 6's are here. These are the 6's and then 12. So go ahead and calculate the probability of rolling a 6 or rolling a multiple of 6 or rolling doubles. We'll work quietly behind you. If you get stuck, go ahead and look up and see what I've done. Questions? How'd we do? Confusion? Feeling okay? Feeling okay to move on? All right. Y'all are doing fantastic. So let's talk about what compliment means. Doesn't mean the math telling you look pretty today. It's not going to do that. It's not going to be math telling you you're smart, but it could do that. I mean, why not? It is basically the probability of something not happening. So for example, if the probability of me going outside and spending any time outside tomorrow is 35%, then the probability of me not doing that is 65%. So you just subtract it from 1 or subtract the percent from 100%. So it's the complement. It is whatever is not happening. So the probability of me getting a dog is about 2%. So the probability of me not getting a dog is about 98%. So it's just the complement. That's exactly what it is. That's what complement means. So this is owning a dog. So according to the American Veterinary Medical Association, 31.6% of American households own a dog. I'm kind of surprised it's that low. I think it's actually higher than that, but I don't know. That's just my guess. I don't know. I'm gonna have to look that up one of these days. We want to know the probability that a randomly selected household does not own a dog. So I want to know the probability they don't. So if the probability they do is 31.6, if I do 1 minus 0.316, I will get the probability that they don't own a dog. So 0.684. So the probability of randomly selecting a household that doesn't own a dog is about 68.4%. That's the complement rule. We are going to be using the complement rule a decent amount this term. So every time I say use the complement rule, you're subtracting it from 100%, subtracting it from 1, depending on if you're using percent or the decimal. Question? Okay. So sometimes it's useful if you don't want to add a whole bunch of things together. Like so, if I added all of these things together, so there's a total of 318,800 households in Hartford County. The probability a randomly selected resident will have a commute time of 90 or more minutes is about 0.015. So if I wanted to know the probability that somebody has a commute less than 90 minutes, I can add up all those probabilities, or I could do 1 minus 0.015. I could do this in my head, but I'm not trusting myself after the whole M&M mess. So the probability of somebody having a commute less than 90 minutes is about 0.985. That is so much easier than adding all of these things up and figuring out all those probabilities. So sometimes you just use the complement rule and just get the opposite of that. Make sense? Feeling good? All right. Ready for 3.3 or whatever we are. We're not going to do that one. 5.3. That's the 5.3. Look at us. We are in the last section. The last section, we have 14 slides to go, and many of them are super fast. We are gonna get done. I told you guys that the 2.5 hour 2.5 hour, however long that one was, those are things of the past. We are not going to be doing them that long. Yeah, I'm gonna try to be nice and not do that. Okay, so two events are independent if the probability of this, we're in section 5.3. I think I said that, but if you keep track of that sort of thing, they're independent if the occurrence of one event doesn't affect the probability of the other. We're going to look at some examples. So they are dependent if the probability of one thing happening affects the probability of the other thing happening. So, for example, the probability of my daughter going out to dinner tomorrow night depends on the probability of her going to work tomorrow night. So if she goes to work tomorrow night, the probability of them going out to eat is going to be less. If she doesn't go to work tomorrow night, the probability of them going out to eat will be higher. So those two events are not independent because one thing affects the other. So that correlation coefficient kind of is helpful thinking about that. If the two things are basically not correlated, then they're probably independent of each other. We're not going to throw that in here, but just kind of getting your brain wrapped around it. So let's talk about some events and whether or not they're independent. I draw a card from a standard 52 card deck of cards and then roll a dice. The events draw a heart and roll an even number. Those two things are independent because the results of choosing the card don't impact the toss of the dice. So those two things are independent because the probability of the one thing happening doesn't affect the probability of the other thing happening. It's another one. Suppose two 40-year-old women who live in the US are randomly selected. So this is the entire US. The events woman one survives the year and woman two survives the year. Those are independent. So it's important to note here, there are a lot of 40-year-old women in the US. It is not likely that you're going to choose two whose lives affect each other, right? If I randomly chose out of the entire US two 40-year-old women, I'm not going to choose, most likely not going to choose two women whose lives affect each other. So these are independent. Next one might surprise you. Two 40-year-old women live in the same apartment complex. Woman one survives the year and woman two survives the year. They are dependent. The reason they are dependent is because their lives cross, their paths cross. Even if they're not friends, their paths cross. For all you know, there's going to be an apartment fire and woman one is going to save woman two's life. If woman one wasn't there, woman two would not survive. Therefore, their lives intersect with each other. So it may be really small difference in that probability, but because their lives intersect at least in some way, they are dependent. So that it could cause a very, very minute difference in those probabilities, but it could be there. So we have to say they're independent. I know, I don't like it either. It's okay. Okay,
So
let's
they are dependent, not dependent.
they're dependent. Because these women's paths cross, because they're living in the same apartment complex, their survival could affect the survival of the other.
So it makes them dependent.
Yes.
Okay.
Okay. So suppose you flip a coin twice. On the first flip, it lands on heads. In the second flip, it lands on tails. Are these dependent or independent? I'm not going to write the whole word out because I'm lazy. They are independent. So many times people will like flip a coin. If you got five heads in a row flipping the coin, you're like, the next one has to be tails. It doesn't. The probability is always 50%. It doesn't have to be tails. It could be heads again. It's not likely to continue being heads. I mean, because law of large numbers, if I keep flipping, it should approach 50% of the time it'll be heads and 50% of the time it'll be tails. But just because I got heads five in a row doesn't mean tails is gonna come next. Those are independent. Are the events earned a bachelor's degree and earn more than $100,000 per year dependent or independent? Now, I'm sure this person's not a teacher, but in many jobs, you're more likely to earn more than $100,000 per year if you have that bachelor's degree. So these have to be dependent. I'm just going to write dip. They are dependent because you're more likely with that bachelor's degree to earn $100,000 per year. Next one. Two 24-year-old males in the United States are chosen at random. Male one gets into a car accident during the year, and male two gets into a car accident during the year. Are they dependent or independent? So there's a lot of 24-year-old males in the US. It is not likely you're going to choose two whose lives affect each other. So these would be independent. So now let's say two people travel 199 between Grants Pass and Cave Junction every day. The probability that person one gets into a car accident on 199 during the year and the probability the second person gets into a car accident during the year, those would be dependent because we traveled the same road every day. Whether or not we encounter each other, you don't know, but there's a possibility we could encounter each other. So those would be dependent. Even if we don't travel normally at the same time, we could end up traveling the same time. So they're dependent, or yeah, dependent. All right. So we kind of looked at that. So the multiplication rule, I call these, whoa, I don't know what happened there. I do, I flipped. And probabilities, I call these and probabilities. If events are independent, if they are independent events, Then you just multiply the two probabilities together. Oh, there's sirens and everything. So independent events, if you have an and probability, look for the word and. If thing one has to be true and thing two, if I roll a two and flip a heads, roll a two on my dice and flip a head on my coin, those would be independent events. And I want to know the probability of both of those happening. I would multiply those probabilities together. This is the multiplication rule. I always say and probabilities because I'm looking for those words in the word problem, and or. Okay. Probability a randomly selected female aged 60 years old will survive the year is 99.186%, according to the National Vital Statistics Report, whatever that is. So what is the probability two randomly selected females, 60-year-old females, will survive the year? So what we're going to do is we're going to say P1 survives and 2 survives. So person 1 is going to survive and person 2 is going to survive. So they both have the same probability. So I would do 0.99186 times 0.99186. So you take the probabilities of each of those and multiply them together. So that's approximately 0.9838. So we have a 98%, about a 98% chance that both women will survive the year, both randomly selected women. You just multiply those together. Because these two women aren't living in the same apartment building, they're independent. Questions on that? Doing okay? Okay. Oh, look, here's the math. I just did the math. Sheesh. All right. Suppose I flip a fair coin. Bleh. I flip a fair coin twice. The probability you obtain a heads on both flips. So go ahead and math this one out. Probability that you flip a heads and then flip another heads. So, so probability heads and heads. This word and. Okay, so you should have had 0.5 times 0.5. So your probability is approximately, it's exactly 0.25. So you have about a 25% chance of flipping heads and then heads. How'd we do? Do good? Okay. All right. So this is real math. This is real math that manufacturers do. So a manufacturer of exercise equipment knows that 10% of their products are defective. They also know that only 30% of their customers are actually going to use the equipment in the first year after it's purchased. This is all that New Year's resolution stuff. You know, people buy their exercise equipment and then it just becomes a really expensive coat rack. So there's a 1-year warranty on the equipment. They want to know what proportion of customers will actually make a valid warranty claim. So we need to know that the probability that it is defective and it was used. Probability it was used during that year and the probability it was defective. So somebody has to use the equipment and that equipment's defective. So manufacturers do this because they're trying to determine, is it worthwhile for me to pay for that more expensive part that's going to fix this defective thing? Is it worth it? Or, is it not likely we're going to get claims? This happens a lot. So you would say 0.10, that's how many are defective, times 0.3, that's how many people will use it. I can do this in my head. Why am I using my calculator? So that is 0.03. So there's a 3% chance that a person will make a valid warranty claim. 3% chance somebody's going to use it and it's defective. So remember our empirical rule, anything less than 5% happens less than 5% of the time is considered unusual. They're probably not going to fix their equipment. If it's only 3%, and I think a lot of these people will just be like, oh, it's broken, and then they won't make their claim anyway because we're lazy. It's like when I get something, like I order something from Amazon and it doesn't work or it comes broken or everything, I have to determine, did I spend enough money on this to make it worthwhile for me to return it, or am I just going to throw it away? So I think exercise equipment, though, you might make the warranty claim. All right. So this one is, we're looking at 4 people. So it's the same thing before, except for it's 4 people. I would like you to calculate this one. So we're looking at the probability. So this is randomly selected female. We want to know what's the probability 4 randomly selected females will survive the year. So person 1, person 2, person 3, and person 4. So we'll go ahead and math that out. Ooh. I'm just going to write 1 and 2 and 3 and 4 survives. There we go. I'm hoping. Oh, there's more than one way to do this, but or if your brain isn't fried from a really long day with heat outside, you might have done this. If you got approximately 0.9678, you did good. Pat yourself on the back. Great job. Yep, I see that right there in the chat. Good job. So yeah, about a 97% chance that all 4 randomly selected women will survive the year. So in your calculator, if you don't know how to do if you don't know how to do an exponent, there's this little caret button. I'm gonna pop back over to my calculator. So this caret button right here. So I would do 0.99186. This button right here, it's called a caret. That's your decimal. So just push the caret and then put 4 and hit enter. This caret raises it to a decimal. Because we're going to need that on the next screen. I don't know if you flipped it to the next screen yet. We definitely don't want to do 0.9986 times 1,000, or 1,000 times itself. So we want to, oh wait, this is at least. Okay. This cannot be said enough times. We're going to do at least probabilities. At least. Every single time you see the words at least, you are going to use the complement rule. And I'll show you why in a second. I'm going to say it again. Every single time you see the words at least, use the complement rule. Every single time. And I'm going to show you why. So we're looking for the probability that at least one male out of 1,000 will die during the course of the year if the probability that a random selected 24-year-old male survives the year is 0.9986. We want to know the probability that at least one survive, or at least one dies. So I'm going to write this out. So we're looking for the probability at least one dies. Stats is just full of, it's like, there's no way to get away from the people dying thing, problems in stats, because one of the more commonly ways stats is used is for actuarial work, which is people and insurance companies determining, like safety. And so it's all about, unfortunately, about death. So the probability that at least one dies is the same as the probability that not 1,000 survive. So we need to know the probability that not, whoa, I just both survive. Really weird. What the heck is wrong with me? I don't even know. Let's just erase it all. What did I do? That's what happens when you talk and write at the same time. Okay. So the probability at least one dies is the same as the probability that not 1,000 survive. So remember when we're using the not, we use the complements. So I would do 1 minus the probability that all 1,000 survive. This is what it's going to look like. So we would do 1 minus 0.9986 to the 1,000th power. This is what you're going to put into your calculator. So we do 1 minus the probability that all 1,000 survive. 0.7536. So there's about a 75% chance that at least one will die out of those 1,000. Questions? We have one more slide. Look at this. 6:15. We have one more slide. Questions on this? I feel that I just feel that somebody has a question. I also feel that you don't know what that question is. You don't know how to word what that question is, but it's in there. I feel it. Could tell by your laughter that I'm telling the truth right here, isn't it? You're like, I have a question. I just don't know how to ask it. I think I have another example. Do I? Yes, I do. I have another example. This is something I made up, so it's probably not true at all. The next example. So we're going to do another one, and hopefully this helps. Among 21 to 25-year-olds, 29% say, no, maybe this is wrong. I didn't make this up. 29% have said that they have driven while under the influence of alcohol. Suppose that 3 are selected at random. What is the probability that at least one of them has not driven under the influence of alcohol? So trust me when I say it makes sense to write it out the way that I wrote it out in the last one. So once again, you see the at least. Every single time you see the words at least, use the complement rule. I told you that statisticians don't deal in absolutes, but in this case, we are dealing in absolutes. If you see the words at least, use the complement rule. So first we have the probability that at least one, at least one hasn't. I'm just going to write it like that. The probability at least one hasn't. Okay. So that is the same thing as the probability not all, well, all 3 have. Can you see that that means the same thing? Can we see that those two things mean the same thing? So not all 3 of them have driven under the influence of alcohol if at least one hasn't. So this is the same thing as 1 minus the probability that all 3 have. So this 1 minus the probability that all 3 of them have driven under the influence of alcohol. So it's 1 minus 0.29 to the 3rd power. That's approximately 0.9756. So there's about a 97.5% chance that at least one of them hasn't driven under the influence of alcohol. I'm telling you, in this particular chapter, in chapter 5, the most common questions I receive are with the at least probabilities. I am happy to answer them. Please, when you get stuck, I say when, not if. When you get stuck on the at least probabilities, send me a message. I will write it out like this for you. I will break it down for you so you can see it. But every time you see at least, use the complement rule. And once again, when you see and, you're multiplying. When you see or, you are adding. This is my last slide. Wait, is it? Yep, the next one's blank. This is it. Look at this. We're at 6:20. This is like super early for us. We are done. I have nothing else for you. We are still recording though, so if I have questions about any of the stuff I've taught tonight or anything else that you think should be on the recording, then go ahead and ask it now. Either type it in chat or ask it. These are recorded questions. Wait, real quick though. Real quick. I'm guessing you probably want me to talk about this. I sent the email out today. This is the final project, and there's the important dates here. So I'm just going to go through this real quick. I'm going to spend like 5 minutes on it, and then we will end our recording. So notice that we have 5 different assignments that go with your final project. One of them is due August 6th, so that's pretty soon. And then the rest of them are due later. So the reason there's 5 different assignments, and look at I have a J here instead of an H. That's just a cute little typo there. So Tuesday, August 6th, I want a project idea proposal. Now, I am not expecting you to have a fully fleshed out project idea. I'm not expecting you to say, I'm going to collect this data, and I'm going to show this, and I'm going to use this analytical method, and I'm going to have these graphs. I'm not looking for any of that. Basically, I'm looking for you to say something like, I'm going into the medical field, so I want to see if there is a correlation between drunk driving, I don't know, no, let me say cholesterol rates and age. I don't know. Those are the things I'm going to collect. Or I want to see if there is a correlation um, between weight and number of times that they visited the doctor in the past year. So I just want you to just pick 2 variables that you think are interesting. I'm going to tell you that most of the time, the best projects I get are the ones where people choose something that they are passionate about, something that's really important to them, either a cause that's important to them, or maybe something that's in their future job, or something to do with their degree. The least successful ones are usually the ones that people pick something completely random or something completely. And I'm not saying you can't, and I'm not saying there's not. I've had some really good projects with things like coffee and number of hours people sleep at night. There's been some really good ones, but the best projects I have are the ones where people choose something they're passionate about. So what you're going to need, let me see if I can find it. Oh, so what you're going to need is it's in here somewhere. You need 2 variables, at least 2 variables, and 50 data values for each variable. These things need to be 2 things that you think are related to each other. So you could do something like, a lot of people do the 50 states, where they'll do something like poverty and they'll do something like poverty level and teen pregnancies per state. That way they can have 50 data values. People do stuff like that a lot of times. So you need 50 data values and at least 2 variables. And you're going to analyze them. Don't worry about analyzing them yet. You're going to learn more math so that you can do that. And this is doing really weird things. So you're going to learn more math, so you'll have more ways to analyze them. I'm not looking for that with your proposal. All I want is your ideas. And feel free to give me 3 different ideas, and I will give you feedback on all of them. I just want you to be thinking about it, and I want you to throw some ideas at me. If you throw ideas at me that are actual ideas and not just, I don't know what to do, give me ideas. I'm not giving you credit for that. You'll get the full 5 points if you say, I'm interested in doing something regarding welding. And I don't know anything about welding, so that was a really bad example. But then say, I want to look at maybe the relationship between these two things. And just throw something out. Say, I'm really interested in childhood obesity, and I want to look at childhood obesity rates and can you think of a second variable that might be able to help me? Whatever you're passionate about, whatever you're interested in, this is the place for you to shine. This is the place for you to actually talk to your friends and put the time into the research. Number two, so that's the first assignment. That's due 8/6. I just want something, anything. That it does not have to be fancy or formal. Just type out a sentence or two. So
Do
the
we
data,
email you the proposal?
what was that?
Or do we just respond to your email with for the first part?
No, there's an assignment that
Oh,
you
okay.
just click on the show work button and just type it directly in there.
Okay, perfect.
Okay, the data set. On 8/15, you need to give me your data set. You need to collect your data. I am not looking for any graphs. I just want the raw data. That's it. Give me the raw data. And then there's 2 questions here. I want you to tell me how was the data obtained, and I want to know why you find it interesting. You need to find this one interesting. I actually want you to tell me why you find it interesting, why you chose this one. So these 3 things are due on August 15th. And the reason I have you give me your data set almost 2 weeks before it's due is because I don't want you to wait till the very last minute to work on this. You need to be working on this all along. I will this goes in the data set, goes in as a lab grade. I will allow a late pass on the data set. So I will set that up so late passes can be allowed there, but there will be no late passes for the written report or the presentation. So the written report and the presentation are due the last Tuesday of the term. So they're due that last Tuesday. And the written report, I'm not looking for writing 121 quality writing, but I want to be able to, I have to be able to understand what you're doing. I'll discuss a little more what I'm looking for in the written report later on. And in the final project folder, so there's a folder, let me find it. My Zoom meeting does weird stuff. So there's a folder right here, project assignment folder. And look at this as a student, because I see lots of stuff you don't see. Assignments and lessons. Okay. So in the project assignment folder, there's some examples here. So there's examples here that you can look. These are presentations that I've had in the past that students have turned in. 2 of these earned extra credit, and the others, they were all passing. I'm not going to say what grades they got or which ones earned extra credit or which I liked the best or anything. I bet you probably could figure it out if you look at it. But these are some good examples of what students have done in the past. All right. And the last grade that you're going to get is commenting on 3 of your classmates' presentations, and they have to, that's not what I want. Stop it. Okay, continuous scroll. That's what I want. So you just have to comment on 3 of your classmates' projects, and they need to be actual comments, not just good job, or this looks really nice. I want you to actually give them, like, really comment, nice, meaningful comments. There is an opportunity for extra credit, and I wrote right here, and basically if you go above and beyond what is taught in this class in any way, you'll get some extra credit. And there's just advice on the 3rd page. So, and a couple of different things that I will be looking at. You have to have one hand calculated formula. That's something on this last sheet. Don't hand calculate a correlation coefficient. Please don't. Don't hand calculate standard deviation. Make it something like a z-score or a mean. So make it something simple, but there has to be one hand calculated thing. All right. I'm not going to go into this anymore. Send me emails, send me messages if you have questions about that. All right. I'm going to turn off the recording.